With medical breakthroughs happening at the fastest rate ever, you'd expect a donated organ to be sustained with something more sophisticated than an esky, right? Wrong. Thousands of liver transplants occur annually, yet the most widespread method for preserving livers is still static cold storage. This technique involves placing the liver in a preservative solution, sitting it on ice within an insulated container. Not only does this damage the organ, it leaves clinicians with little insight into how well it's functioning. So what if we could keep the liver working between the donor and the recipient? Machine perfusion is a promising approach that circulates oxygenated blood around the liver to support it outside the body. Clinically, it's used for up to 24 hours, which is enough time for a basic assessment, but not nearly long enough to rescue the astonishing number of donor livers currently deemed unsuitable for transplantation. That's where long-term perfusion comes in, which can not only preserve good livers, but also give marginal livers a chance to be revived. Existing viability criteria weren't designed for use beyond 24 hours and rely on slow, often conflicting tests that offer limited insight, especially as perfusion time increases. So to make use of extended perfusion, we need better markers to continuously track liver health over multiple days. Fortunately, there's a clinically used dye that can do just that, indocyanine green, or ICG for short. When injected into the bloodstream, ICG is exclusively uptake by the liver. There, hepatocytes move it from the blood into the bile, making it a direct indicator of how effectively the liver clears substances. The faster the ICG clearance, the better the patient outcomes post-transplant. But despite ICG's proven value in predicting patient outcomes, there's still no continuous real-time method to apply it to machine perfusion. So to fill this gap, my project focused on 3 key aims. First, develop an optical sensor that could continuously measure ICG during liver perfusion. Second, validate the accuracy of the sensor against a spectrometer. And third, use this sensor to investigate whether ICG clearance reflects liver function and metabolic rate. Starting with the sensor development, I placed a laser and a photodiode on either side of a tube containing blood to detect how much light gets through. A wavelength of 805 nanometers was chosen for the laser because ICG absorbs light most strongly in this region. This ultimately means that the more ICG in the blood passing through the tube, the less light that reaches the photodiode. By tracking this change over time, we can measure how quickly the liver is clearing ICG from circulation. To complete the sensor, I placed these components in a custom printed clamp-on housing to easily attach it to tubing. However, before using the sensor in real perfusions, I needed to test these key components. First, I confirmed the laser's wavelength using a spectrometer by aligning the laser light with the detector and taking repeated measurements. The result showed a clear peak at 805 nanometers, exactly what's needed for ICG detection. Next, I tested the photodiode's linearity by incrementally reducing the light intensity with absorbance filters and recording the response. The results showed excellent linearity across the absorbance range. So now that I knew the sensor was working correctly, I needed to validate the readings by comparing the sensor measurements to a spectrometer. Firstly, blood samples were taken at fixed time points after an ICG dose for spectrometer analysis, whilst the optical sensor recorded continuously over this same period. Secondly, to make the readings comparable, the datasets were scaled between 0 and 1. Lastly, an exponential decay curve was fitted to both datasets and then compared. This graph shows that the sensor data, shown in orange, very closely aligns with the spectrometer data, shown in blue. The sensor was even able to capture an initial mixing phase that was missed by the spectrometer. And finally, as the true test of the sensor in practice, we administered ICG doses to 2 different livers over 4 different days to see if its clearance would reflect the function. We found that as perfusion time increased, the clearance rates slowed significantly, indicating a decline in liver condition. Then, since temperature affects metabolic rate, I tested whether ICG could distinguish between perfusions at 20 degrees and 36 degrees. Clearance was shown to be 3 times faster at 36 degrees, showing ICG's ability to track metabolic activity and function throughout perfusion. By expanding this optical approach to other wavelengths, we can measure additional key markers like bilirubin and oxygen consumption during perfusion. Additionally, thanks to the non-invasive clamp-on design, these sensors can easily be added to existing liver perfusion systems, and even adapted for other organs like the kidneys, heart, and lungs. Together, these optical sensors could bring us closer to a future where organ assessment is continuous, automated, and informed, giving more patients a chance at a successful transplantation.